Welcome to the Aerospace Advantage podcast, brought to you by PenFed. I'm your host, Heather Lucky Penney. Here on the Aerospace Advantage, we speak with leaders in the armed forces, industry, and other subject matter experts to explore the intersection of strategy, operational concepts, technology, and policy when it comes to air and space power. This week, we're taking a deep dive into quantum technologies, what they are, how they work, why it matters, and what steps the U.S. is taking to realize the benefits of this emerging technology. If you've read through the Space Force Future Operating Environment, you know that quantum technologies offer incredible potential for communications, sensing, networking, and computing. The first nation to move this technology from the lab into practical operations will have a distinct advantage in the ongoing competition. So, to help us navigate and make sense of this complex subject, I'm thrilled to welcome Jay Lowell, the Chief Scientist of Boeing's Quantum Systems. Jay, thanks for being with us.
Thanks, Lucky. It's good to be here, and I'm happy to talk about one of my favorite subjects, quantum technology.
Excellent. So we also have our senior fellows at the Mitchell Institute for Spacepower Center of Excellence, or MySpace. So Charles Galbreath, or SOX.
Hey, Heather, great to be back with you.
Thank you. And Jen Reeves, Boots.
Hey there. So glad to be here.
Excellent. So let's start high level about the area of quantum and what it could mean. So when you look back at the history of humanity, major advancements like the printing press, computers, internet, and now artificial intelligence have fundamentally changed the way we share and use information. Will we be adding quantum to that list? And how might it change our approach to information?
So, Lucky, I think that when future historians look back at this era of the 20th and 21st century, they're going to say that quantum science and quantum technology already have made that fundamental change. And a lot of that is in ways that we don't really recognize as being quantum. All
Lasers.
of computers work on semiconductors. All semiconductors require us to understand how quantum mechanics works. Otherwise, they wouldn't work. All lasers are built on an understanding of how we manipulate aspects of a quantum system. And so the compute that we use, the lasers that drive that information across our fiber optic networks already have been changed. What we're talking about today, the quantum technologies that are part of the future, are taking that and turbocharging it. We're looking at quantum computing, quantum sensing, quantum networks that are allowing us to manipulate those quantum systems, not just take advantage of their properties. And that manipulation, that active manipulation, is really what is going to enable us to drive forward. I think of it a lot like we're in the early days. Again, thinking back to history, DARPA sponsored the earliest work that led to the internet in the 1960s, 70s.
60s, yeah.
That work was focused on a single application. How do I make sure that information can get to a command and control bunker, right? It really was about how to guarantee message delivery when we thought that some of our communication wires were going to be down. We didn't have a way to do that. We thought of one wire, one way. That one application really helped guide the research, but fundamentally, what we see today is nothing like that. We think of that as just the tiniest sliver of what the internet is and how it works. Quantum technologies are like that at this point. We understand that we can use quantum computers to compute really interesting things like properties of materials or like how to solve complex trajectories of fluids, things like that, that we understand how they're useful. And so we have a good use case. But we're just scratching the surface. The future is limitless in what we're going to be able to take how we're going to be able to take advantage of our ability to manipulate these quantum systems and put them to use in a way that drives economic and national security benefit.
I really like how you differentiated how we use quantum technologies today that's fairly mature and very everyday, where we're benefiting from their behaviors and properties and characteristics, to the future of quantum, where we're actually controlling, manipulating, and exploiting our ability to really control those quantum states down to the qubit level. And that there's something different between using superconductors for today's advanced computing to what a quantum computer will be. So for those in our audience that want to geek out some more, could you describe specifically, when you say quantum, what are you really referring to? What does this technically mean?
So the quantum that I am thinking about today is really these three areas of quantum technology: quantum computing, quantum sensing, and quantum networks. Those three areas all rely on our ability to fundamentally manipulate the quantum mechanical state of the atoms or the atom-like system, the qubit that is part of that. In a quantum computer, we're using that to perform a computation, to perform a calculation of some. And the amazing thing is that because these properties are decidedly different than a regular computer bit, we can do very different kinds of calculations and much more efficiently. But it also has a corollary to this. The quantum networks that need to connect these computers have to fundamentally carry that different kind of information, which doesn't necessarily sit on just a regular pulse of electricity. I have to think about encoding that information into a photon, connecting it to the atomic system. And in doing that, what I'm setting up is a condition where these quantum computers can collaborate. I can use that joint characteristic of
That
their
entanglement.
quantum, that entanglement sets up this joint characteristic of these two computers so that they can now collaborate seamlessly on a calculation much larger than either computer could do on its own. And that's where, so what I want everybody to kind of think about here is that in having the ability to manipulate these quantum properties, again, these characteristics of the individual atoms that we're isolating from the rest of the world and using their properties. By manipulating those, we're either going to use them to compute something, to get an answer to a problem that we want. We're going to use them to sense some aspect of the world around us, or we're going to use those two things to communicate and to set up this joint collaboration by things that are separated over long distances. And that collaboration has power and unique capability in and of itself. Those are three powerful capabilities that we really are going to build on with these quantum technologies, and that's where they have the promise of really changing the way we do things operationally.
So let's kind of go backwards a little bit and talk about, because you've mentioned some of the properties of quantum particles. I'd like to maybe do a little bit of school right now to review some of those things so folks really understand what you're saying when you're talking about entanglement, when you're talking about non-locality, when you're talking about coherence or superposition and wave functions, right? Because these are all things that are pretty important to understanding the reality of and the technical challenges, but also the technical potential for what you're talking about. So when you talk about networks, that really requires entanglement.
Yes.
And that originally requires that those two particles be together so they can be influenced in the same way, right? Before you separate them?
No, not really.
Okay.
What it requires, so look, entanglement is one of the most difficult concepts to understand in quantum mechanics. It's one that troubled people as smart as Einstein, and frankly is one that I struggle with to make sure that I understand exactly how it's going to work in a particular situation to perform a particular effect and function. So our audience is not going to walk away here with a great understanding of entanglement. I don't think I'm not a good enough teacher of this kind of stuff. And frankly, it's an unrealistic expectation. But it is okay to get an intuitive understanding of how this works is something that is really that's something that we can try to hit today.
Okay.
So to do that, what we really are talking about is I need to have a way to transmit information about one atom state. So we'll talk about atoms. When I say atoms, I'm generalizing.
Okay.
I really don't mean, I can mean an individual atom, but I don't have to. So when you want to connect those, you need a way for a single photon that encodes the state of that atom to connect to another one.
Okay.
So I need a transmission line, I need a fiber optic line, or I need a free space telescope to send that information. And I need the ability to receive that. So they don't have to be local in the sense that they don't have to be touching, they don't have to be in the same room. But I do have to have a link.
And that's how you entangle them.
and you use that link to entangle them. Now, once you have established that link, those things are entangled as long as they can hold on to that quantum information. And that, you mentioned the word coherence. That's a technical term, but the easiest way to think about that is I can hold on to that information as long as I don't have something that interferes with it. So if we're walking around trying to have a conversation on our cell phone in the neighborhood, there are times when all of a sudden the message gets garbled. That's because you're having channel interference or signal path interference, and so you're not able to receive the information. In a quantum system, that happens not just when you're trying to receive it, but once you have it, you can have things that interfere with it that same way.
And change
and so
the
it
state.
gets garbled,
Okay.
and when it gets garbled, it's not as useful.
Okay.
So the key is I can get that entanglement, I can distribute it to two things, I can then move them. There is theoretically no limit to how far apart they can be, provided I can hold on to that information in a way that it's not being interfered with.
So when you separate them, do you still need to maintain that optical link?
I don't need to maintain that link.
So
Okay.
how do you physically separate them?
I can have one of the, so what we envision in a space-based quantum network is I would have a ground station in New York, and I'd have a ground station in London, and I would have a satellite that's in between. I would take my systems, I would send my photons down from that satellite to New York and to London. So I've had a link now between them, and I've established a means that New York and London now have these entangled particles, but the satellite keeps moving and now can no longer see New York and London. So as long as they can hold on to that information, it's still entangled.
So New York and London are entangled, and they can share information between themselves about the quantum state of the two entities,
Yes,
even though there's no
no
physical
active link.
connection.
There's no active physical connection between the two. And the key and again, what I want to emphasize here is what that enables is the ability to act collaboratively.
Right.
You can use that information in a collaborative sense. There are three real ways that we think of that. There are three, and I'm going to be very general in this. I can use that information collaboratively in a way that actually obscures what I'm trying to do. So I can think about that like information security. If I don't want somebody else to know what I'm doing and I only want the other party to know what I'm doing, establishing this link that enables collective behavior is a great way to do that. It's the equivalent of saying, I've given you a code that says when I raise my right hand, that means this. And when you then receive or hear that I've raised my right hand and you observe your system, you'll know exactly what that means. So it doesn't matter that it is a quantum system. It really is about I've established a way to have that collective behavior. And I can use that to secure the transmission of information between those two parties. I can also use it, as I said before, to collaborate on a computation. The computer in London and the computer in New York, to be able to be part of a really big computation, I can distribute this entanglement that says, okay, I'm going to connect the part of the calculation that's going on in London to the part of the calculation that's going on in New York by setting up this collaboration between them using entanglement as that resource. Okay. And then lastly, I can use it as a means to sense, to improve the ability of sensors that are located. So if I want to take a telescope in London and a telescope in New York and point them up into the sky and look at a very faint object up in that sky. Let's say that's, for example, a satellite that doesn't have anything turned on. And all I'm getting is the tiniest glint of sunlight off its surface. If I have those two telescopes and they're entangled, when those photons, when that light scattered off that telescope or off that satellite hits those telescopes, it takes the tiny signal in London and the tiny signal in New York. And because we've said, hey, collaborate on signals that are like this, all of a sudden it turns those two very faint dim signals into one big bright signal.
Okay.
That's, again, without getting into the math, that's how these things work. And that's the amazing power that they offer.
So I'm really intrigued by this because I thought that when you measured a qubit, you collapsed it and you destroyed the entanglement. The relationship goes away. Is that not true?
That is true, but you don't have to measure it when you get it. You can hold on to it and you have it become part of another process, and you don't measure it. You measure the outcome of that process. So that entanglement is embedded into that process.
So we're measuring the output from the process, and we're able to retain the entanglement
Buried into that process.
Even though we're seeing that bright signal from space because of the collaborative properties of the entanglement.
Yeah, we talk about that as injecting that. We would inject that entangled photon into the stream of photons that goes into the telescope. And when we do that, we essentially only measure the output of the telescope. We're not measuring the entangled photon directly.
Fascinating.
So could I ask one more geek question?
Totally go for it.
So I think most of our audience is familiar with binary. Either a circuit is either on or it's off, and we use that way to create computers, right? But with quantum, it's more than just on-off, right?
That's a superposition piece, right?
There's multiple states. So is there more than how much information can actually be entangled in a quantum system? Are we talking about 8? Are we talking about 4?
That's not really the right way to think about it.
Okay.
The better way to think about it is what you're really doing with entanglement is taking an imprint of the quantum information that's in one system and sending it to the other quantum system. And that really is not a bit measure. It's a state characterization.
Okay.
And so you're trying to produce that collaborative state between the two. Again, you're trying to produce that collaborative behavior, which means you need to have this state and this state joined in a particular way.
Okay.
So
Jay, I'm just going to say this is the reason why I'm glad you're the chief scientist over there, because right now this is all PFM as far as we're concerned. We're trying to make this accessible. But it also goes to show, I think, for our listeners, the level of technical difficulty of what your team is doing, because this is something that's really hard. And it also, I think, demonstrates why it's so crucial that we maintain the strategic advantage. So I want to pivot the conversation. If you mind that I hijack this?
Look, it's actually probably best because I can go down a rabbit hole and
we will go down those rabbit holes.
We'll never get out.
We will gladly go down those rabbit holes with you, because I think there is a value to understanding the basics of the science, because it also shows that it isn't magic, that it is actually technically sound.
Yeah, one of my favorite quotes from physicists is that any sufficiently immature technology starts out seeming like magic until it becomes readily accepted and understood. Until we have a way to conceptualize how it works, it is that lack of understanding is what we call, as people historically call, magic, right?
Yeah.
It is our word to explain the thing that we don't understand well enough to have an explanation for. So as we see things more and more, they become intuitive and they don't become magic. They just become tech.
What is service? It's defending what's right. It's protecting people you will never meet. It's something that lasts a lifetime. PenFed has served the military and their families for over 90 years. We look forward to 90 more.
Yeah, no, absolutely. So I'm sure we'll get back to some of the elements of the science and how all of that works. But I'd like to pivot a little bit and say, what are some of the practical applications as far as the Space Force is concerned?
Yeah, well, I've pointed to one of those. I think this idea of using an entanglement network to link sensors to be able to have them measure very faint effects is something that, for things like space situational awareness or space domain awareness, those are things that are sorely needed, especially as the envelope that the Space Force is responsible for is going
all
from
the way out to the moon and beyond.
Just geo all the way out to beyond the moon. That is a huge expanse. And so our ability to make active measurements of things that are out there is really going to be restricted and limited. So we have to think about ways to help the sensors that we have work better. And quantum technology is one of those things where we can think about making those sensors work better because they'll collaborate better. Again, that network enables that collaborative, that collective behavior, and that is the power that network brings.
And that's really interesting because you used a telescope as an analogy to monitor light. But I know that from the air side, we've also been concerned about quantum radar. And that has seemed like it is not a viable technology. But now I'm wondering perhaps it is.
No, the difference really comes down to that the radar photons the energy that's in a radar is the photon energy is so small that it takes so much effort to produce the injectable signal into that. It's actually easier to just add power to the radar. Once you start looking into everything that has to happen to make a radar work, you run out of advantage really quick because all of those other things make the trade-off not worth it.
Well, so that makes me feel better from the air side, but let's get back to space. Boots, communications, quantum communications, what are we looking at there?
Well, I think that the technologies writ large could transform the way the Space Force does so many things: communications, navigation, sensing, how we synchronize forces, protecting information in contested environments. It just goes on and on. And I mean, and then more specific applications, I mean, precision timing, missile tracking, inertial navigation, the alternatives to GPS, right? Capabilities that might be particularly valuable in GPS denied or electronically contested environments. And then if we start looking longer term, some of the complex operational analysis that are tied to larger efforts happening in space, right? Orbital operations, battle space management. Ultimately, the Space Force exists to provide this information advantage to the joint force. And I think quantum technologies could fundamentally reshape how information is protected, transported, sensed, and ultimately exploited. I think this is a game changer.
But we can't just let quantum be pixie dust that just gets spread everywhere. We have to be very specific about the types of quantum technologies that will apply.
Yeah, I think Jen hit on it when she talked about the security of it. So if you're talking about communications, for example, if two atoms are quantum entangled and there's nothing physically connecting them other than whatever's happening in the quantum realm there, that is a secure form of communication that has a low probability of interception, a low probability of detection, which is absolutely critical for military communications, as well as not just communicating, but also the command and control between the ground station and the satellites themselves. And so that level of security is something that quantum would really enable. I mean, when we talk about where the future is for space operations, the Space Force just released their 2040 operating environment, and they talked about this concept of unrestricted spectrum warfare because RF is going to be jammed so much and cyber is going to be intruded on and spoofed, et cetera. But if there's a way through quantum to provide a secure means of communicating, that's going to be a significant game-changing advantage.
Now, is that, Jay, is that secure quantum communication, is that just a quantum key? Is that encrypted, or is that through this entangled network?
All of the above. So good question. There are the earliest ways that that'll be demonstrated is the formation of keys using quantum mechanics to produce that key and transmit that key. There are more advanced protocols that rely on entanglement that go beyond that. There are also one of which we're investigating because we think it's really important for the authentication part. Right? It's not just important that you have a secure means of transmitting information from point A to point B. You want to be sure that you understand who the party is, who is making that transmission at the other end. And so one of the things that we've been looking at is a protocol called quantum position verification that allows us to provide guarantees about where that information was transmitted from that cannot be spoofed without.
Basically, it's a positive identification that I know, no kidding, it's Jay that's sending me the signal, not Boots that's sending me the signal. Is that a sort of an accurate way of understanding that?
So let me back up for a second.
Sure. Okay.
So this protocol, quantum position verification, is one where it allows us to make guarantees about where a message is being transmitted from. And without the ability to falsify that location, which today you can do. You can just say, look, I'm in Peoria, I'm not in New York, but I'm going to say I'm in New York, and nobody will be able to tell the difference. This allows us to determine unambiguously that you are in fact in Peoria and not in New York. And in fact, not just in New York, but not in the same building or even the same room that we want this to be. So it's not that it is Jay sending it, it's that I know Jay's supposed to be in the podcast recording room sending his message, and this protocol says Jay's actually on mic 3 in the podcast recording room recording his message, transmitting it.
That level of fidelity and granularity is just astounding.
So it's, again, an example of how security is, we're going to be able to reimagine the way we architect security in these information environments.
So how mature is this technology? I mean, we're talking about networking and entanglement and quantum compute and so forth. I mean, where are we on that TRL level? Are we all getting Q1 iPhones next year?
Only if the iPhone Q1's the size of a suitcase can only transmit information to your neighbor when he's awake and at night, but at night. So this is all relatively low TRL.
Mm-hmm.
So it's interesting for compute. We actually, in our company, we talk about not TRL in terms of the computers, but solution readiness level.
Okay.
How ready are they to provide a solution to a particular problem? So we've created a framework that allows us to assess that for quantum computers. For quantum networks, the TRL is low. It's in the 3 to 4 range, but it depends on whether you're talking about, actually it's in the 4 to 5 range, whether you're talking about over a fiber, or whether you're talking about free space, or whether you're talking about to space. Those TRL definitions are going to vary depending on the technology.
Now,
and
when you talk about
sensing is different as well.
Yeah, it does really depend on the type of application and the technology and the modality and all of that.
All of that, the specific technology. When Boots talked about inertial navigation technologies, that's one of my favorite areas as well. We've been working on that for a long time. We've done fielded demonstrations, which some would say, oh, well, that means it's TRL6, but that fielded equipment that we used for a demonstration is not in any way like a product. It's a research piece of equipment. So it's like a research TRL6, not a product TRL6. It's like a product TRL4 or TRL5. So we're getting there. We're rapidly advancing the research grade and demonstrations, the demonstration articles and the research articles and the prototypes to rapidly advance up that TRL level. But they're not products yet. And that will take another round of development to get those. But what I expect to happen is as those demonstrations go, we'll start seeing, like we did with a lot of early technologies like UAVs, where you'll get prototypes that'll start being grafted into the operational use because the value will be so clear and so relevant. And you'll start to see a blurring of that line as it advances.
So when it comes to, for example, this quantum communications or networking, what is the kind of information that we would transmit? And what's the bandwidth? What put this into what the user would experience and how they would use this kind of capability?
Yeah. So the bandwidth of the network, like any communication network, the bandwidth of the network or the throughput of the network matters, right? I mean, if I'm sitting here looking at my phone, I want that video to show up when I want it to show up. I want the live stream to show up when I want it to show up. And that's a function of that bandwidth and that capacity of that network. With the quantum networks, that's the same way. And it really, again, it depends on what I'm going to use that network for, right? I say that the bandwidth matters for a regular communication network, but I measure that differently if I'm streaming than if I'm emailing, than if I'm doing an IM. I don't need a lot of bandwidth to make an IM useful, but when I start sending an email, it depends on the size of the attachment that matter, and when I'm live streaming video, I really care about that bandwidth because I need all of it on and I need it all the time. I think there are other properties that really matter for quantum networks that are important. And one of the ones that I want to highlight is actually stability. Quantum networks require an inherent stability that really is kind of mind-boggling when you think about it.
Now, when you say stability, are you talking like it's got to be, drilled to the floor and not experience any vibration? Or are you talking about stability in that the quantum state stays stable and so it can't have the interference that would disrupt its coherence? I mean, when you say stability, what do you mean?
Let me give you an example. So if I need, and I said earlier, if I want to send quantum information from New York to London, and I'm going to send that over a satellite link, the stability that that network has to have means I need to understand the path that that information takes from ground station to satellite to ground station. I need to understand the length of that path to about the thickness of a human hair.
Oh, that's pretty granular.
And with that stability comes one of the other things that Boots talked about, which is time dissemination. Time dissemination and quantum networks are really, you can say, well, I can use a quantum network to disseminate time, but the other way to think about it is I need that ability to disseminate time to be able to have the quantum network function properly. They really are part of the same problem. They come to how do I make sure that I understand the stability of that network path. That really fundamentally is what is going on here, is that network requires a stable understanding of how it is configured and how it functions.
So would early applications of this networking really be in quantum computers because we can control that? Or are you really seeing this London to New York through a satellite be absolutely attainable in the near term?
I think the near-term applications are really going to focus on information security. And the reason for that, look, the reason for information security protocols is they don't require lots of extra hardware beyond just the ability to sense and read and kind of measure those photons, right? And that makes standing up those kinds of networks and testing them for that purpose to be something that is much more attainable than having to connect quantum computers. The first connections between quantum computers are going to happen in closed, same building environments where I'm connecting the computer in room 1 with the computer in room 2. And we're starting to see that work happen in the quantum computing realm. But doing that over a space-based network is going to take longer.
Yeah.
What we're thinking about, our internal thinking in this, when we're recording this in May of 2026, is that information security and timing are kind of those early things that we'll see coming out of the building of these networks. And when I say timing, I mean, factors of 1,000 better than we can do with our current GPS time dissemination.
And that's going to go so far for warfighters across all domains.
Yeah.
In today's rapidly changing world, innovation is essential. At BAE Systems, we design and deliver cutting-edge technologies that solve the defense industry's toughest challenges before the need even arises. From advanced research to fielded solutions, we anticipate our customers' needs, envisioning, executing, and delivering critical technology at mission speed. Learn how we're shaping the future of safety and security at www.baesystems.com/fastlabs.
So Boeing is investing its own R&D funding on a project called Q4S. What will this project demonstrate, and when are we going to see it?
So Q4S is a self-funded project that we have at Boeing put together to help put us on this path to establishing these global space-based quantum entanglement networks. So that project will demonstrate a protocol that is called entanglement swapping on a self-contained satellite. By demonstrating that, we are essentially getting at the core action that would happen at any satellite on an eventual network. That swapping protocol has to happen in order for me to move entanglement from A to B to C. And by doing that demonstration in that kind of environment, we are going to take that and really evaluate its suitability for these long-term networks.
When you say entanglement swapping, you're talking going from New York to London to Paris?
That would be an example of where I would need to use entanglement swapping in order to make those steps.
Wow. So Q4S is a satellite program, so you're going to be demonstrating this in space. When you transition from the lab to an operational environment like outer space, you have less control over the variables. Can you describe some of the variables that you expect to encounter with Q4S as an on-orbit demonstration that you could easily control in the lab?
Yeah, that's you've hit upon one of my favorite sayings to my team, which is space is not a lab. They are not the same. Doing a quantum physics experiment in a laboratory is hard. There are hundreds of people across, thousands of people across the world who do PhD granting research doing quantum experiments in labs. We're going to do an experiment in space that would probably grant somebody a PhD at a university anywhere around the world today if they accomplish it in the lab.
You're going for your postdoc.
So
that is ambitious. Like, that's amazing.
And to do this, we have to control for the fact that the hardware that is designed to do this kind of stuff, the lasers, the polarization rotators, the photon detectors, the electronic control systems, all of these things. If I'm a graduate student and I'm trying to go put this together for an experiment, I can buy a lot of off-the-shelf things that can do that. But the laser that I'm going to buy is typically big, and I need a kilowatt of power to plug it into the wall. And the detectors that I'm going to use are cryogenically cooled, which means I need another kilowatt to power those. And they're going to sit in a vacuum chamber that's actually the size of a household refrigerator. And I'm going to put it on a table that is the size of this table that we're sitting at in this podcast room, 3 feet by 6 feet. We don't have that kind of space on our satellite. We don't have a whole lot of mass that we can carry up, because carrying that table up, that's a lot of weight. Every kilogram we try to put up in space costs a lot of money to get it up there.
It's a lot of fuel. It's a lot of payload.
And if I have to power it with that much, that means I've got to have a lot bigger satellite to produce that much power. So what we've had to do is miniaturize all of these technologies to take and adapt all of these. We've had to do massive adaptations to things that are available and would be used to do this in order to make an entanglement swapping demonstration that is much, much more efficient than anybody else's.
So when you're in space, though, I wouldn't expect microgravity to be an impact
it's not
on
gravity,
quantum. But how about radiation?
It's radiation
and thermal?
And it's the temperature variation.
Yeah.
So a laboratory, even if it were just in this room, the temperature of this room changes a few degrees a day, right? Realistically, the building HVAC system just takes care of that for us. We don't think about that. We just count on it.
It's not
right?
plus 270 minus 270.
In our case, for the satellite, we're changing 3 Celsius every minute over basically railing between temperatures and switching direction of that temperature change every 45 minutes as we go in and out of the view of the sun. And the radiation environment is something that we have to account for as well, because electronics don't like radiation. So we've had to account for that and make modifications and shield the electronic circuits that they work so that they will be successful. So there's a lot of engineering that goes on top of this. And that's why my statement is space is not a lab. You've got to treat space like space, which means you've got to treat those environmental differences. You've got to actually come back and manage that thermal, which means we need control systems that account for the changes that thermal change is going to impart. For us, again, remember I said we need to know the length of that network really precisely. Well, because we're doing this all on our own satellite, we actually need to know it even better than that length of a human hair. We're about 1/10 of the width of a human hair that we have to control. Our detectors have to be, we know from our laser to our detectors, that length has to be controlled to that well. And as the temperature changes, that board flexes and expands. And we need to have a compensation system that tracks that and accounts for that, which we do. We've built those control systems that wrap around all this that say, we know what these changes are ongoing, and we can account for those, and we can make them work.
Mind-boggling.
So can you help us understand how that all lives together on what we all know as sort of normal satellites? Tell us more about the satellite itself, the orbit, the design life, and then how all of that gets wrapped in, again, to what the rest of us think of as a normal, nominal satellite.
Yeah. So to set the stage, that what we're deploying this experiment in a 16U small satellite. So that is realistically, that's about the size of a large dorm refrigerator. Or a dishwasher is about the right size, right? It's about 40 centimeters by 40 centimeters by 80 centimeters.
I'm just astounded by the complexity required by the single satellite, but you're not stopping there. So you'll put a greater constellation to be able to do some of this swapping, and that has got to increase the complexity, correct?
Where we go from here, we want to demonstrate this protocol on a single satellite. The next thing we need to do is demonstrate it across a link between a satellite and something else.
Okay.
So whether that's a satellite and another satellite or a satellite and a ground system, we have done designs for both demonstrations. And in so doing, we think we understand a path forward for either of those. We'll probably do one at a time and then connect all of that together.
Wow, that just blows my mind. It's the technical challenges that you are facing and solving and implementing in a way that provides a viable path forward to a usable product. There is so much that is going on there. But, we're not the only nation that's looking into the benefits of quantum, because there's, as we mentioned before, this global competition to gain that advantage.
Boeing's self-funded effort, Q4S, which will be the first satellite that puts the U.S. on the map as a satellite. The U.S. has had space missions that have been flown. Those have all been on the International Space Station or something that flew on the X-37B. Those were not necessarily all networking, but they were quantum systems that were deployed to space. So again, I'm trying to draw a distinction here. The geek in me has to be a little bit accurate every once in a while.
Yeah, so I'm reading, though, that despite us not being fully, autonomously spacefaring with quantum on its own platforms, that we're still probably leading overall in research depth, maybe private sector innovation, certainly with the university ecosystems and venture investment, right? I mean, we're so decentralized in how we do things in the States, whereas we see other big governmental efforts. So I still feel there's a difference, and I think the U.S. is making a big difference, leaning forward in a more decentralized kind of way. And you guys are right on the forefront.
Thanks for that. And I think to comment on that, if one were to say, what is the level of competition in quantum computing? That answer is going to be very different the world over than is the question of what is the level of competition in quantum sensors versus quantum networks. What I was really talking about and focusing on here was how have space-based quantum network demonstrations been taking place, and how is that progressing? And that is just one of those many measures. And to your point, that decentralization both works for us and against us in the U.S. It can allow for us to rapidly make headway on a particular area when these disparate groups collectively decide that's the thing that they want to go do. We can make incredibly fast progress, and we have a lot of that infrastructure in place, the academic infrastructure, as you point out, the national labs, the defense labs, all of these things provide a base, a base on to build that on. But it can work against us when all of the attention is on something else. We might be prioritizing internally, or as that loose collective, as you describe it, that distributed, disseminated group. If their focus of attention is somewhere else, we might not be as up to speed in one particular area.
But like you said, there's different aspects of quantum. There's sensing and networking, and correct me if I'm wrong here, but the benefit of going to space is in networking. Because of the spherical nature of the Earth, if you want to connect 2 points and you need that optical connection initially, you need to do that via space. Is that right?
So space is required for quantum network to go beyond kind of the
Line of
length.
Line of sight.
So it's
Or
really
fiber.
the length that I can send and transmit that quantum information, which through a fiber optic is about 65 miles.
Yeah.
Whereas if I go through free space, I can make that several hundred miles.
Right.
If I go through space. So there is a strong, very strong trade-off at the system architecture level to make quantum links go through space
Okay.
to make that network function.
Thank you. That's really important. So, socks and boots, what's your perspective on this facet of the competition and the implications if one side makes these quantum technologies operational first? Because how Jay laid that out is very compelling.
Yeah, absolutely. So, and I'm really glad he distinguished between the different types of quantum technologies here. A military or a nation that can have that secure communications, that can have that certainty to the level that he's described, that's just going to make war planning and the execution of combat operations that much more effective in the future because of that security. And then if quantum sensing comes to fruition in one form or another, that's going to make things like
When, not if.
okay, when. Thank you for the correction. But that's going to have a significant impact on stealth technologies, right? And how we think about penetrating aircraft or other systems. So there's huge ramifications for this if we're not on the leading edge of that.
So, and if I can, I want to take it one step further from what Charles is saying. We have these different applications that we all have just heard about and talked about. I think what the key thing is going to come down to one word, and that's operationalization. Who is going to operationalize any of these first? And that's where I think the real benefit is going to come. Not just that we have figured out how to do it, but that we are actually then doing it, right? That we figured out whatever other random kinks in the system that we're going to find as we no kidding lay this into an operational configuration to be used by warfighters in the field for the appropriate purpose. And I think that will bring a significant hurdle as well as understanding and code breaking the tech originally, right? Getting this laid in to be operationalized. I think
This is getting it out of the lab and into space.
Absolutely.
Right.
So
Absolutely.
if I can, this harkens back to one of the things I said earlier, which is when you say operationalize, you have to really define what that application is that is being operationalized. So I don't think that first is necessarily the real true measure of win here. The true measure of win is who operationalizes the impactful.
Right.
It's a race to operational impact that is realizable. That's the way to frame this or think about this is as we operationalize it, that it means that we've worked out the kinks and we're reaping the benefit. We're reaping the impactfulness of that operationalize. We're reaping the impactfulness of that stuff.
Jay, I really like how you framed that. So as we wrap this up, I'd like everyone's thoughts on what do we need to do to ensure the United States is the first to operationalize the impact of the potential of quantum technologies, be that networking, sensing, compute, whatever.
The U.S. has done a lot of things to do this. The Department of Commerce announced over $2 billion of investment into quantum computing companies that is going to drive a huge amount of innovation in the field. And there will be impacts in not just quantum computing, but on quantum networking that come out of that work as well. So there is lots that the U.S. government has done. There is lots more to be done. I think the way I think about this is we're at the start of a journey. We're in the internet equivalent era. We're in those first baby step demonstrations of value and working out how we capitalize on that particular use case that we understand today. What we don't see past us is that really amazing future where we start innovating on top of that and create truly unimaginable things that are going to drive us in unknown and really exciting directions.
I think there's some mechanics out there, some processes that we can that we can lean on that help bring things like help move the ball forward. Public-private partnerships, right? We need some government investment.
The clear demand signal for business to invest as well as government investment. Is that what you're getting at?
Yeah, absolutely. And that helps when the demand signal helps our private industry partners actually invest more, do more, because this isn't easy, right? Getting the talent. Yeah, getting the talent out there, right? I mean, we are four smart people sitting here chatting about this, and it's been a little bit of a tussle to understand what these concepts are and what's actually happening. And so we've got to educate a workforce to help bring these concepts to bear with operational applications. I think there's a lot that we can do. And I agree with Jay. We're just at the beginning, and it's going to be an exciting time to be part of this.
Yeah, I think step one is help demystify quantum. There's leaders in Congress and the administration and in the military that recognize the value here. But I think most people would struggle with the conversation like we did earlier today about what really is quantum. And it is practically magic because it is so advanced from what we recognize today and understand intuitively. So I think there's got to be some additional education about what it is and what the benefits are. And then that will drive some funding. We like to quote the right stuff, right?
No bucks, no Buck Rogers.
Absolutely, absolutely. And so I think dedicated, concentrated funding on specific efforts to achieve quantifiable objectives on the path to delivering the impactful quantum technologies. And Jen, I'll 100% jump on the bandwagon of STEM. This is not a short journey. We're at the initial stages of what will be a very long and very prosperous journey. And in order to make sure that we continue down that path, we've got to invest in the education capability of our next generation and the generation after that. So we need to encourage them and cultivate that science, technology, engineering, and mathematics education as we go forward on a national level.
Jay, thank you so much for your perspective, because I think the impactful capabilities is really what we need to focus on. We've seen too many of these advanced technologies like AI and autonomy and quantum be tossed around like it's pixie dust because people don't really understand it. And I think we face a risk of, if we don't understand the technology, then we might fund and invest in those pieces that wouldn't be impactful.
Yeah.
And
the other danger that we run into all the time is that without focusing on the impact, you don't know what it is that you have to measure and demonstrate. And it is technology only advances at the rate, in my opinion, and this is something I've said before. Sorry, this is going off on a tangent, but
no, go for it.
Bear with me for a second. There are two things that really govern the rate at which a technology goes. One is the rate at which the development occurred. That's where your Buck Rogers analogy really drives directly. But the other thing that really comes about is it only can advance as fast as one is able to communicate in a language that is common to people on the other end of that discussion,
right,
what it is used for and how it is useful. And the best way to do that in the early stages of a technology is to ground the discussion in data. And by having that communication be clear and grounded in data, we don't fool ourselves into thinking that we have something that is just pure magic. We have the ability to look at and see the actual data that shows us and grounds that discussion in something that we are able to understand better. Even if we may not understand how it was done, we can understand and ground what was accomplished in a way that helps us then imagine how to use that. Those two things, that funding and that communication, really will govern the rate of progress, and both are important.
And I like how you talked about the communication being grounded in the data piece, because we also have to avoid snake oil.
Exactly.
And that could be just as disastrous to valid efforts, because if in one case you go, oh gosh, that didn't work, then would you assume that none of it will?
Right. Do you poison the well?
Exactly. So Jay, thank you so much for being here as part of the communication piece.
Yeah, this has been a pleasure. It's a great conversation to have with you guys.
Super helpful. And socks and boots, thank you.
Thank you, Heather. And Jay, thanks so much. Great discussion.
Jay, thanks for an amazing hour.
Yes, exactly. And so for our listeners, if you do want to geek out on some of the science, we did write a quantum primer. It's a 3-series primer. We'll put those in the show notes, and we look forward to seeing you next time. And with that, I'd like to extend a big thank you to our guests for joining in today's conversation. I'd also like to extend a big thank you to you, our listeners, for your continued support and for tuning into today's show. If you like what you heard today, don't forget to hit that like button or follow or subscribe to the Aerospace Advantage. You can also leave a comment to let us know what you think about our show or areas that you would like us to explore further. As always, you can join in on the conversation by following the Mitchell Institute on X, Instagram, Facebook, or LinkedIn, and you can always find us at mitchellaerospacepower.org. Thanks again for joining us, and have a great Aerospace Power kind of day. See you next time.
You talked about the internet and how it's being used in so many different ways than it was originally intended. The same thing can be said for space-based remote sensing, for
everything.
space-based positioning, navigation, and timing. Right, those areas have just boomed after their initial government use, and when you put it in the hands of consumers,
I mean, in the modern world, I mean, look at drone use.
Yeah.
In the Ukraine, that is not what drones were built to do. But look at those are being adapted rapidly in a completely different, changing way, and how they control them has been adapted rapidly to account for that environment. This is how technology evolves. Technology evolves by getting to the point to where there's an element of what it is that's demystified. And once it's demystified, it's like, well, what if I do this? It seems to behave this way. If I do this, shouldn't it do that? And isn't that an interesting thing? Well, let's go try it. And somebody tries it, and lo and behold, it does that. And then they go, well, that's useful. I can make money with that, or I can have an operational impact with that. And so it spreads and it keeps going. It's a snowball.
Yep.
And then Uber Eats is delivering autonomously my dinner tonight in a cooler that rolls down the street with no operator anywhere nearby.
Right.
It'll holler if it gets messed with too.
Yeah. And in the future,
Those are all over little college campuses.
you'll pay with a quantum bank.
Exactly. And let's everybody say it together. Operationalization. There's the word of the day.
Yeah.
Operationalization.
For sure.
That's a mouthful, certainly. I think I choked on it at least twice.
And me more so.
That way I remember who's where.
What socks are you wearing today, by the way?
I've got retro rocket 1950s style.
Oh, I love that. Oh, those are good socks.
They are good socks.
Oh, you got
like-
airplane socks on too.
All right.
Sweet. I think I saw an F-100 there. Maybe a Sabre.
B-52,
Oh, is that a
biplane,
B-58? Maybe a Hustler.
maybe.
Or no.
I
That
don't
looks
know.
more like an F-105 because of the profile of those socks.
I don't know. I just bought them because they were airplanes.
I like
There we
that.
go.
I like that.
I mean, I did have to do all of that contour identification back when I was at the academy, but that's so long ago, I don't think I remember half of them. Actually, I don't remember a tenth of them. So to set the stage, that what we're deploying this experiment in a 16U small satellite. So that is, realistically, that's about the size of a large dorm refrigerator. Or a dishwasher is about the right size, right? It's about 40 centimeters by 40 centimeters by 80 centimeters. Sorry, I'm a physicist. I use centimeters, right? So 39 inches, or 30, no, sorry. What's that?
I'm reminded of.
You said it's a 16U CubeSat?
Yeah.
So 4x4x4.
We're doing advanced math here.
It's not 4x4x4. It's an elongated.
Okay.
We're just going to stop
No,
after
let
you.
me. I got to do
okay,
this because I got to
okay.
prove to myself that I can.
Did you ever see that one George Washington SNL where they're
Oh, yeah.
like,
Yeah.
what is a kilometer to a mile? No one knows.
No one knows. 1.6. So what's 1.6? Why do I care?
So like 1 by
Right.
2 by 8.
So it's 40 centimeters is about 16 inches, right? So it's 16 to 18 inches by 16 to 18 inches by about 35 inches. That's a 33, 34 inches. That's about the size of the satellite.
Okay.
And our payload itself is about 10 liters. So again, me in this metric, right?
How many milk jugs is that?
It's a little over it's 1.5 milk jugs. Right,
So-
it's a gallon and a half.
There we go.